Hey, welcome back to Mini Rust in Rust. This is episode 44. My name's Andy. We are writing a Rust-like programming language in Rust. It's an interpreter, though, not a compiler, at least for the moment. So that means things work a bit differently. But we're hacking our way through it. We're doing it very test-driven. And we've been trying to push towards doing some type checking. And here's an example of a thing that should work. We should be able to declare a variable x, say that it's an i32, put a value into it, and then the code says, like, give me the value of x, right? This is what this last bit means. And when we're type checking this code, the type checker should return i32 as the answer here. So let's just double check that right now it doesn't. I'm very sure that it doesn't. By making this into a proper assertion, and it should be a type constraint i32. So these at least are like types exist for this. And first of all, it doesn't return one thing, it returns a vec. So is that really right? I guess it's like type checking. Yeah, I guess it is. It's type checking. All right, so this needs to be a vec, and the first thing will be a unit if I'm right. Let's see. So please format my code. All right, so the first thing is going to be, so the first statement in this thing has no type. Why is it not working? Oh, no, okay, it's a type syntax tree. All right, so, yeah, okay. So, how are we going to do this? I just want the type. I don't want to say, like, all the other stuff that's actually coming back, because what we're returning from type check is a typed syntax tree. So I guess what I want to do is be given a tree. I just want to say what's the type constraint on it. Do we have something like that? I'm not getting any completion from that. Let's imagine we have a type syntax tree like this of type leaf, and it has a type constraint of i32, and let's also say it has some kind of leaf token. Of a certain kind. Int sounds sensible, and a span of like something like that. Right, so basically what I'm saying is I'm just creating myself a typed syntax tree to see whether I can then ask for the type on it. Yes, I can. Is that actually allowed? Is it public and all that? Yeah. That means I can ask for the type here. And then, oh, hang on, the point is we can't map because this is returning a vec. That's our problem here. Yeah, so we need to iterate in order to be able to map. And then collect. So maybe we can break this into multiple lines because it's getting a bit blah, blah, blah. So let's just say let types, which is a vec, equal this whole thing. And then assert that it's what we wanted it to be. And okay, and we can just, I think, just take references and then make this be a vec of references and we'll be okay. No, we need to hold on to this thing. Or I don't know. move them or something, but I think this makes sense, right? We make a tree of typed, we make a typed syntax tree, because that's what type checking does. It makes us we already had a syntax tree from out of the parser, and then we evaluate all the types and stick them in, and now I've got a type syntax tree. That's what this is. And then I just want to get all the types out of that because I don't care what's actually in the tree. Now we've got a vector of types, or rather a vector of references to types. If we did into iter, then we wouldn't need to take a reference. We could just take them. And now, yeah, this will be slightly neater looking. Get rid of my test code. So now we have a test that looks right and will fail. Like this. There it goes. All right, so as I predicted, the type that comes back when we ask for the type of X is any, and it should be I32. So the reason this fails is really because this thing fails. And let's imagine that there's a piece of code here so that this test actually makes sense. So basically, when we ask for the type, or ask you to type check a leaf token, we should look up in our some kind of environment what X is and tell you the type that we have for it. And in the future, that will somehow be changeable by future code that adds extra constraints to X. But we're not thinking about that yet. So for now, it's a really simple thing. But we're not even passing an environment in to this type check leaf function. So I think what we need to do is imagine that some kind of environment exists. We're going to call it a type environment because we already have something called an environment, which is the environment that's used when you're evaluating code. So that's the environment that has values, variables, variable names. It maps variable names to values. Now I think we need a completely different thing called a type environment or something like that, which we can add. Let's look at the existing environment we have and see what methods we have. Oh, we have get and set. Yeah, so we want the same thing. So we're going to set, and what does it take on the left? String. So I guess just the variable name. So we're going to say that X is a I32 and I32. We're going to pass this environment in to type check leaf, and the answer should be I32. And that means that R to do is no longer valid. So we obviously, this doesn't compile yet because we haven't got a thing called a type environment, and we don't take an environment argument in our type check leaf function. So let's make ourselves a type environment. It's going to be quite similar to environment. So I think I'll start with that. Make a copy. And maybe this should be called an eval environment or something later, but for now, let's have it be a type environment. Have this one be type environment and that one be environment. I don't think we're actually going to need values, which is kind of interesting. So a type environment can be created. It's a hash map of string to type constraint, maybe. We'll see. You can get them. This is not giving me compile errors because it's not yet, it doesn't yet exist. So let's just try and make it exist. You can set it with a type constraint. We should rename this to I guess type. Right, what's it complaining about? There's some tests here. I guess we can use very similar tests. So when you try and get something that isn't there, then it should return an error. Interesting. I guess that makes sense. Like we should never try and look something up that isn't there. So now if we set this to be the type constraint I32, this thing to be, let's make it a different type constraint. Like, I don't know, F64. When we try and get it out, we get out what we put in. So this is just giving us an environment that we can pass around. By the way, both this environment and the evaluator environment, which for now we're just calling environment, are going to be nested structures. We haven't done this yet. Okay, this checks that things are missing. Things still give you an error even when some things exist. Yeah, at some point, environments are going to have a parent environment. Yeah, we did call sets, but it's unused in real code. That's why it's warning us here. Yeah, an environment's going to have a parent environment, and when you look things up in it, it's going to also look in the parent and find them in there. But so far, we haven't got to code that requires that. We're doing very strict test-driven development, so we don't write code that isn't needed to pass our tests, which means that we get to keep things nice and simple for as long as possible. Right, so now type environment exists. Let's bring it in and make it mutable so we can set things on it. And now let's make type check leaf take an environment. Like this. I guess maybe a reference to an environment would be sensible. And if it's a symbol, that's what this is, then we need to know the symbol name. So I guess the symbol name is going to come from the file contents, right? So we need some more code in here. So we're type checking a leaf node, which is of type symbol. So let's get the symbol name from the file contents, and we're going to slice it based on token span. That's what span is. It's how you can look up in the file contents and find the symbol name. Now we've got a symbol name. We're going to look up that symbol in the environment. And this is a symbol name's already a stress slice. Oh no, it's a star. Wait, yeah, I missed my ampersand here. Okay. And I think that's it. Oh, get returns a result. So I guess if we question mark it, are we done? And oh, okay, we messed about with span. So if we just clone that here. All right. Is it that simple? There's still errors. Oh, all the other places where we call type check leaf, I guess, are going to fail. So type of an int literal is it? So this doesn't need anything in its environment. So we can just say, make it be a brand new one. Pass it in. And any more? Same again. Do I want this gap? I think I do. All our tests get longer as things get more complicated. I guess to some extent there's no avoiding it. Oh, we should pass in a reference to that. Okay. That's in a reference here. It's going to be a mutable reference in some situations, I'm pretty sure. Okay, so now here's the actual place where we type check. Like, this is the production code where we call type check leaf. And I'm pretty sure type check tree is going to take in this environment as well. Oh, wow, look, good completion. Thank you. So that means we can pass it straight through here. And then who calls type check tree? Oh, that should be environment. Okay, who calls type check tree? Maybe some tests. Lots of places called type check tree. Lots of places. Okay. All right. Start with the first one. Right. So this is a real type checking code. So let's tackle this first. So I think that the type checker, which is what this is, should hold on to the global environment, and as well as the file contents and this kind of iterator of syntax trees that it's working through. So for now, we'll just call it type environment. For now, we'll just call it environment, and in a way, it's like it's the top level global environment. Now we can pass it in a reference to it as the first argument into type check tree. And now I think this makes sense. We've got to fix all the tests, and we've got to construct that environment when we first create a type check. So where are we? Oh, lots of other places which call type check tree, including type check tree itself. So that's quite straightforward. We can just pass environment in to our recursive call, and then probably loads of other places call it, and we're going to need to pass it into them too. For example, type check operation should just take one in. I mean, it's kind of making me wonder whether, with environment and file contents, maybe this should be methods on some kind of thing that holds on to. I guess on the type checker. So we could have a lot of this stuff as methods on the type checker, and then the environment and the file contents would get passed through directly. Yeah, that's something to think about. We won't do it now. So now type check operation takes an environment, which it can then use when it calls type check tree. Like this. No, that should be environment. Yep. Right, where else? Probably most type checking is going to recursively call type check tree. So we're going to need it. Yep. Here, and yeah, it's starting to look, isn't it, like some kind of struct for these things would be really helpful, because we're passing in that pair of arguments in lots of places. Why I'm naturally putting a comma at the beginning there, I don't know. I'm appreciating that autocomplete that just does the right thing. Now, is this in a function that we've already updated? Yeah. Okay, we're getting there, We'll do it here too. Just 15 more errors. Okay, all right, so now we're in the tests. And I presume most of these tests won't be affected. Like type checking this thing, which is a statement. Yeah, type checking a statement should return unit no matter what's in the environment, so shouldn't be a problem. Similarly, presumably these tests, if they're already pass, so here type checking assignment returns unit. Okay, so when we create a type check, we also need to create an environment. And I think it can just be empty. Because if we haven't hit any code yet, there's nothing in the environment. Now, at some point, maybe there'll be modules or something that complicate that, but for now, should be okay. Now, when we call these various functions that we added an argument to, we need to pass that argument in. Like so. Okay, all the errors are gone. How's our tests doing? Previously, 1 test failed. Now 11 tests fail. Okay. They're panicking because the names we're looking up are missing. So which tests are failing? Okay, evaluator tests are failing. Interesting. Okay, so this is because we haven't put these things in the environment. So even though we're trying to test the evaluator, we're crashing in the type checker, which runs before the evaluator. So we need to implement stuff. So for now, I think we could probably just run the type check test that we have and check that that works. All right, so it's failing because this name X is not in the environment. So let's have a look at that. Oh, hang on, that's the wrong thing. So it does not fail. Okay, so this test passes. Oh, we should rename that to that. Let's just check that actually passes. Yeah, so that test passes, but type checking a symbol does not fail. Fails because the name X was never put into the environment, because we haven't actually implemented this thing yet. We've just passed an environment around. And when we manually set it, it works, but where we're expecting this assignment to set it, it does not work. So let's look at, I guess, the type check assignment code, right? And this is where we're immediately going to need to pass in a mutable reference, so a lot of stuff's going to go. Okay, never mind. So here's assignment. No. Where do we type check assignment? Here we go. Type check assignment. It's going to need to take in a mutable reference to an environment. And once we've figured out the type, there's a declared type. When we make this assignment thing, we set the type. Okay, the type of an actual assignment statement is unit, but declared type looks interesting. But it could be optional. So the point is, an assignment either has a type that's explicitly declared, or it has just we figure out the type from the right hand side. So that would be expressions type. And then we combine them together, but we don't do anything with that. So let's combine them together. And actually use that for something. So I'm going to call this resolved type. And if there's a declared type, combine it with the resolved type, and that's going to be the answer. So we're going to match on combining the types. If it was an error, then we do what we did before. If it wasn't an error, we return that type. Semicolon. That should not have that should have a comma, right? Yeah. Nope. Okay. What? Okay. This might not work out. So if there's no declared type, we need an else. We do need an else. It's right. If there's no declared type, then the resolved type is just going to be expression type. Expression dot type. Okay, but with this is like expressions, we need to clone that, yeah, to get hold of the type without breaking expression. So now resolve type is going to be, if there is a declared type, then so let's rename this to something better. So this should be called declared type, right? Wait. Hang on. I mean, it's kind of, let's call it the type from the declaration. So declared type is of type symbol token. So this should be, let's rename this. This should be declared symbol, let's say. Yeah. Let's call it declared symbol here too. And once we've gone and looked that up and figured out that it says like I32 or something like that, now we have a declared type, which we combine with the expression type to get, let's call this resolved type. Well, let's call it combined type. Let's distinguish it from resolved type, which is what we get out of all of these ifs and elses. So if there was a declaration, combine them together, get a combined type, return it. Otherwise, it's just the type of the expression. That is the only type information we have about this symbol. Once we've figured all that out, we're going to set the environment, set it into the environment with, I guess, does symbol have oh look, wow, that's nice. We can pass in file contents, get out the name of the symbol, and provide the resolved type. So when we do an assignment, we set something into the environment saying what the type of that variable is. This seems pretty cool. Is it going to be this easy? Right, so we need it to be a mutable reference here. Definitely starting to think we need to pass. These need to be methods on the type checker. So this, I guess, everywhere we're calling this now, we need to pass in a mutable reference. I wish I'd just used mutable references in the first place, since I knew that this was something like this was going to happen, but I guess I didn't know exactly what. Okay, that means that when we call this, it needs a mutable reference. It's going to happen everywhere, isn't it? Okay. Okay. We could almost search and replace for type ampersand type environment. Would you like me to do gymnastics with search and replace instead of this? Might be more fun. Probably wouldn't have caught any of this stuff. Okay, that's it. That's it. All right, it works surprisingly. I'm surprised. I thought that we were going to hit a problem. Where are we here? But I guess type check next. It takes a mutable reference to self, so we're okay. All right, now is this test going to pass? It does. Wow, that's really exciting. Oh, more tests failed. No, only one more test failed. Checking an assignment returns unit failed because it panicked. Because I guess because our test doesn't actually set itself up correctly, and now it's trying to find the symbol name. It goes wrong, so I don't think it's a real problem. Yeah, we said there was a symbol from 0 to 5, and we didn't provide one. There you go, there's a symbol from 0 to 5. All our tests pass. Right, where are we at? Can it be this easy? I don't know. I never know how long I've been recording for, so maybe this has taken us ages. It feels really quick. So, we made a new thing called type environment, and we held on to it inside our type check object, struct. We passed it in to lots of functions that do type checking. And, yeah, just pass in, pass in, pass in. Pass in, and then when we were type checking a symbol, we went and looked up that symbol in the environment and returned whatever we found there. And when we're type checking an assignment, we got hold of what we reckon was the type of this variable, and we did an environment.set to put it in there. Other than that, it was just passing environment around. And here's where we made our type environment. So it's literally just a hash map of name to type constraint for now. I think it's probably going to stay that way. All right, so provide an environment. Let's provide a type environment for looking up types of symbols. My commit messages are always longer than they're supposed to be. All right, so as a bonus for this episode, since I think it has been pretty quick, let's also look at whether some of these type checking functions can become methods, so we don't have to pass around file contents and environment. So for example, could typeCheckTree be a method? So could it be self.typeCheckTree, don't pass in the environment, don't pass in the file contents, and don't pass in syntax trees because we've got that too. So typeCheckTree becomes a method with no arguments because we've got them all already. Is that going to work? So self dot, now what is the tree called? Syntax trees. No, what? Hang on. What happened here? We messed something up. Yeah, we call next on this. So I guess we will take one argument, which is the actual tree, but we won't take those two. That's a bit more sensible. All right, and then for now, we can just do mutable reference to our environment and this needs to be a method. Needs to be a immutable reference to self, and that means that this needs to live inside the impl of type check. Do we have just a plain impl of type check? Yeah, this is it. This is it. So we're going to move type check tree to be in there. If all this doesn't work, we're going to back out. I think it will. That's my current guess. Okay, so what are you moaning about? Okay, we need to, if we're going to pass in a mutable reference to self into type check tree, we need to not also be hanging on to a mutable reference to self. Is this going to be our downfall? Are we going to need a mini object just for these two things so that these doesn't clash? Let's see. What if we just separate it out like this? I think this will work because tree is not holding on to a reference to self, right? What is tree? Is that a semicolon? Should be. Yeah, tree is just some simple object like a syntax tree. So, okay, so we weren't scuppered by the fact that I was wondering whether tree held a reference to self, so it would stop us having a reference to self here as well, because one of those references is mutable, but we're okay. All right, so we can do the same as this, and then very soon we're going to get rid of this, but I always like to do things as small as possible steps, because of my brain size. So, oh no, type check tree only takes one argument. Self.type check tree, of course. Is this okay? That seems okay. I mean, it's almost like I'm rediscovering that methods exist and forgetting how they work. And you're just coming along for the ride. All right. So I guess anywhere we recursively call type check tree also needs to be a method So all of this stuff's going to need to move in one big whack. And there's no getting away from it. Fine, fine, fine. Right, so type check operation is coming. Let's bring this one. It uses file contents, so let's bring it. Type check leaves coming, type check assignments coming, type check mutations coming, type check whiles coming, type check blocks coming. I mean, it makes perfect sense for these to be methods. So I don't feel bad about this at all. They're all going to take a mutable reference to self, meaning they don't need to take environment or file contents. And then we can call self and not pass in those arguments there either. Like so. And all the places here that we call stuff, we're going to call self and remove the arguments. It's going to work. If it's not going to work, it's going to be annoying because I just decided I had to do it all in one go. But yeah, it's a little bit less code everywhere. So it seems like a good thing. Right. So type check operation takes in a self. This one also takes in, this maybe just takes a non-mutable reference to self. Is that going to cause us problems or be fine? Who knows? And then when it uses file contents, it can be self.file contents. Okay. And this one takes in a mutable reference to self. And again, when it uses file contents, self.file contents, when it uses environment, it's self.environment. Good. Happy or happy. And we don't need these arguments. This one is self.file contents. So yeah, basically anywhere we use this stuff, that was passed down is now part of us, so we need to reference it inside self. Haven't seen anything yet that makes me think this isn't going to work. Glad I did this in a separate commit though. Come on, I can join those lines surely. There we go. Yeah, okay. Come on, the typing's falling apart. Alright, so call it self.typeCheckTree. Even that fits on the same line. This is going to overflow though. No, even that does. Everything does. Okay, so again, recursive call. We don't have to pass these things around. Just feels better, doesn't it? Especially as they're references. Okay, I forgot. I needed it here. I didn't have a self. Now I've got one. There we go. That doesn't fit on one line, does it? Something is preventing the formatter running. I guess it's just the brokenness of everything. Ah, okay, now we've got... This doesn't work. Now we've got to construct ourselves a type checker. Okay, so this is a bit... let's just call it TC. I don't want to overlap. So this is a type check. Does that have a new function? No, we have to actually make one. This is a bit awkward. How many? There's only a few tests that look like this, but yeah, I'm sure there's a constructor for type check. Right? Yeah, here. Oh, I see. We can call a function type check that constructs it and takes in an iterator of trees. So there's a function called type check. Takes in file contents. I guess it's going to need to look like that. Because we're going to be calling this other method. And trees. Do we need trees? I think we don't. So what's an empty iterable? Is that an empty iterable? What about that? What about if we call iter on a slice? No. Okay, what if we made an empty iterator? Is there something like this? Stirred. It's empty. Okay, that seems good. That needs to be a mutable thing, so we can pass it in. Okay, that's surprisingly... Okay, we don't have to test passes yet, so I was about to say surprisingly easy, but we don't know that yet. Alright, here's the next place we're going to call type check leaf this time. It's going to be 12.82. And it makes us an empty environment for us. Where next? Okay, this time we need to set something on the environment of TC. So hopefully we can do this. No, it's not called end, it's called environment. And it's not public, I guess, so can we do that? Okay, so far it's letting us. I guess the file content is just going to be, probably doesn't matter, but yeah. Like that. I mean, it seems to think that's okay. So how many more? Just a couple more of these tests. That seems to be okay with just an empty string. Like so. Are there more of these than I remember? Not convinced we actually need to provide these file contents that are kind of realistic like this, but better to be realistic, I think, than end up with a weird error later that we don't understand. Okay, that was all the tests. So, typo there. Oh, we're down to warnings. Don't need type environment imported in our tests. Right. Oh, no, not git push. Have we successfully refactored our code to make it less verbose? I believe we have. All right, so we just moved all the methods, all the free functions that took in file contents and environment to now just be methods on the struct which has file contents and environment in it, so it makes sense. All this is just horrible diff noise from a relatively simple change. Move type checking functions to be methods. All right, hope you enjoyed the slightly pedestrian bit at the end and the less pedestrian bit of actually type checking things to do with symbols. I think there's more to do on that, but there might be some consequences already. I think there's a couple of other tests that we're probably ignoring because symbols didn't have types. But yeah, the really interesting part, which I really don't know how it's going to work out, is when we have, say, the return type of function influencing the type of a symbol, because we know, for example, that it's like an intish type, but the return type of the function tells us exactly it's an i32. So that means throughout the rest of the function, it has to be an i32. And then we need a decent type error to come out of that when it's not. So, yeah, looking forward to gradually figuring that stuff out. I think basically the next few videos we're going to be looking at to-dos in the evaluator and the type checker, knocking them off until they seem okay, and then I guess the project after that. Once things seem like we have the basics of a programming language that works, it will be filling in all the missing parts until we have a useful programming language. And then there'll be a decision point after that, I guess, if we get through that, of do we start doing more difficult stuff like generics and things like that? Or do we consider it a useful thing that is finished, or just a thing that we've had enough of? Anyway, let me know what you think. Hope you've been enjoying this series. Let me know. See me on Mastodon. I'm at Andy Balaam at mastodon.social. And just wanted to remind you of one set of videos before you go. So if you've been watching these and thinking that I only do like live coding videos, you're right at the moment, but in the past I have done more kind of lecture style things. One of my most popular series of lectures I made ages ago, so it's a much younger me, is about Scheme, which is a programming language, a Lisp programming language, which really got me excited about, I guess, kind of self-describing code, meta programming, programs that describe programs. I don't know how to say it. Anyway, metaprogramming. Let's just say metaprogramming that is exactly the same as programming. So if you're interested in having your mind blown, if you haven't done Lisp before, check out the first video, Scheme 1, Feel the Cool. These are all on video.infosec.exchange. Let me show you my public profile, video.infosec.exchange. My name's Andy Balaam, and you can find them on there, or they are on YouTube as well. I hope you enjoyed. See you next time.